Now, we talked about calculating energies of chemical reactions previously, and we wrote some equations out, included the delta H in those thermochemical equations. Remember that? And Hess's law uses this concept. Hess's law says the energy for any reaction to take place is the same whether it's done all at once or done in steps. So think about this. If I stand here at the end of the bench and I walk across the room to the other end of the teacher's demo area, it takes a certain amount of energy. If I chose to do that in steps, and I start at the same place, I go at the same rate, but I stop, we could measure how much energy that took, and then if I continue at the same rate, we could measure the energy for the second part, and if we add them together, it should be the same as if I just made it in one trip. That's what Hess's law says. That if we can do things in steps, it's the same energy as if we do it all at once. So this is really useful to us in chemistry, and for those of you going into engineering, this will be really useful to you. Because you may be asked, how do I build this reactor to contain this reaction? And you'd say, well, I need to know how much heat's going to be generated so I can have adequate cooling supply. So we can calculate information before we actually go and do something. So what we do is kind of a puzzle. And we're going to flip equations around and add them together to get the energy of the overall reaction of interest. So here's the rules. If you reverse the equation, we change the sign. If we multiply the coefficients, we multiply the delta H. If we cancel something from each side of the reaction, it has to be in the same physical state. So let's look at this problem. Calculate the delta H for this reaction. NO gas plus oxygen atom yields NO2 gas. And we're asking, what is my enthalpy change? Well, let's look at the information we have. We have 3 other reactions, and we know the enthalpy information for those. So I think of this as a puzzle, and I call this my target equation. I am trying to build the target equation using this information. So the way I do this is to look at what I have on the reactant side and the product side in my target. Then I look at where those pieces might be in my available information, and I manipulate things till I get them where I want them. So let's look at this. My first equation has 1 mole of NO gas on the left-hand side. In my target equation, I want 1 mole of NO gas on the left-hand side. So if I use this equation as written, it will give me that first reactant in the position I need. So I'm just going to copy this equation down as it's written. So ozone gas plus NO gas yields oxygen gas plus NO2 gas. Delta H is negative 198.9. The units here are kilojoules per mole. So when I look at this now, I now have the NO gas that I need in position, just like in my target equation, and I have 1 mole of NO2 gas on the right-hand side, what I also need. If I look at what's left, I have ozone and oxygen, which I don't need in there. So somehow I need to get rid of ozone and oxygen, and I need to get my oxygen atom in there. So let's look for the next piece. My next piece can help me with the ozone. So if I look at this equation, this has 1 mole of ozone in it. I want to get rid of 1 mole of ozone in what I'm working with. Since the ozone is on the left-hand side, I need to put 1 mole of ozone on the right-hand side to be able to get rid of it. So the second equation, if I turn it around, it can be used to cancel out the ozone. So I'm going to flip this around. 3/2 oxygen gas yields ozone gas. And the enthalpy for this, because I turned it around, I changed the sign. So it's now 142.3 kilojoules per mole. So when I look at what I've done here, I now have 1 mole of ozone on the right and 1 on the left. So I can cancel 1 mole of ozone. No, it was negative 142, and I turned it around, so now it's positive 142, because I reversed the equation. Okay, if I had used it as written, it would be negative. So now I need to get rid of, I have 1 mole of oxygen here and 1.5 here. So I can cancel out 1 mole of oxygen, and right now I have 1/2 mole of oxygen left because I've canceled out 1 mole of oxygen. So now I am missing the oxygen atom that I need, and I've got 1/2 mole of oxygen that I don't need. My 1/2 mole of oxygen is on the left, so I want to get rid of it. So now looking at my third equation, it has 1 mole of oxygen on the left. It has 2 moles of oxygen atoms on the right. So if I turn it around, I will have oxygen atoms on the left where I want them, and I will have oxygen gas on the right where I want to get rid of it. But the amounts aren't right. So if I look at this, I'll say, well, I'll turn it around, and I'll divide by 2. So when I do that, I get 1 mole of oxygen atoms in the gaseous state yields 1/2 oxygen gas. Now, I change the sign. This was positive. I'm going to change the sign to negative, and I'm going to divide it in half because I'm dividing that by 2. So I now get negative 248 kilojoules per mole. So now I've canceled out this oxygen gas, and I have the oxygen atom that I need in my target equation. Now if I look at this, everything is canceled except what I wanted in my target. When I add this all up, I get NO gas plus oxygen atom in the gaseous state yields NO2 gas. Now all I have to do is add these enthalpies together. Delta H is negative 305 kilojoules per mole. So when I've added this all together, I now have answered the question because I was able to use the equations I was given to make this one, and now I calculated the delta H. Yeah, there was nothing hiding really. So it's kind of a puzzle, and it takes practice. Some of the puzzles are easier to put together than others. Okay, this one was kind of a low end of a medium one. The next one for you to try is a fairly simple one. Just go ahead and do this next one at your seats. Okay, just take a minute, do that one at your seats.